Yeah, thank you all very much. Thank you for inviting me here. And, I was not sure I should even be here because this is not a talk about black holes, really in any direct sense at least. So I thought, maybe anyway, but the organizer said, no, that's fine. So here I am. Okay, and my title is JT Gravity in deSitter Space and its Extensions. Now I'm also embarrassed for the following reason. The talk is not very different from my strings conference talk, which is in fact a half an hour talk. So if you just want to go to sleep and hear the more condensed version, you can just do that. There's nothing really new except at the very end, which I'll try to talk about 3 dimensions, which is really exciting. I've expanded the talk a little bit because I got 45 minutes, but we'll see. So feel free to actually just interrupt me. This is a nice workshop, so it doesn't have to be very formal. Okay. This talk is based on work done, 2 papers. One with my former students, Kanu Nanda and Sunil Sake. Kanu is a postdoc at CMI and Sunil is at Kyoto. And another paper, this was an earlier paper, another paper which came out recently, which is with also 2 of my current students, Indranil Dey and Akashdeep Roy, as well as Kanu and Sunil. Now there are a lot of important references, I won't be able to do justice to them, but 3 in particular were influential for us, rather influential in our work, so I would like to mention them here, including a very nice and old paper by Mark Heno, and then these 2 more recent papers, which looked at JT gravity in deSitter space. There's also an important paper of Kotler and Jensen, who look at the problem more from the path integral formulation. What we will do today is study the system in canonical quantization, and of course, as you know, there is an important tie-in between the 2. Some of that will come out. I will use aspects from from path integral quantization going back to these earlier papers in the talk as well. But anyway, this is an important set of papers as a kind of complement to what I'll discuss. Finally, there are 2 papers which appeared more recently in the run-up to strings in a sense. These 2 papers pointed out that in fact we hadn't analyzed the most general situation. And so you'll see there's a class of solutions which we are not included in our quantization. How to include them is an interesting question, and I will not address it here, but I think it needs to be addressed to complete the study of the whole problem. Okay, a paper appeared around the same time as ours. We tried to coordinate, and that's with by Norihiro Izuka and Sunil Sake. And what that tries to do is, in deSitter, in 2 dimensions, you can have this situation which is actually not allowed by various energy conditions in higher dimensions, which is you can have a bubble of deSitter 2, okay, which asymptotically is anti-deSitter. And that's very interesting because we believe we can understand anti-deSitter more deeply, and so the idea is using that kind of a geometry, which is called a centaur geometry, can you understand aspects of deSitter space more deeply? And this idea has been around for a while. There's several people who have worked on it, but this is also an important paper which came at about the same time. Okay, so much for references. So this is the plan. I'll start with an introduction and motivation, tell you about the classical solutions in this system, then turn to canonical quantization, and depending on time, then turn towards extensions of JT gravity, a little more about a path integral understanding of what we learn in canonical quantization. What we learn in canonical quantization is that there are actually an infinite number of physical states in this system. One of the states in particular is very well understood through path integral means, which is the Hartle-Hawking state. The other states are not so well understood, but we'll see for some class of them at least we get a somewhat limited but still very useful understanding through path integral techniques. So I'll talk about that a little bit, I hope, and then turn towards holography, which is actually rather interesting. How do we understand what we learn through the bulk canonical quantization in holographic terms, and then end with conclusions. Okay, so to get going, Jakob-Teitelbaum theory is a very simple theory of 2-dimensional gravity. There are no propagating degrees of freedom in this system, no analog of gravitons. So you might ask, it's so simple, why even bother to study it? Now, in the context of deSitter, so there's an anti-deSitter version of Jekyll-Teitelbaum, which, as you know, has played a rather important role in understanding near extremal black holes and so on, and the connect with the SYK model and so on has been very, very enriching for our field. But here we'll be studying the deSitter version, and in the deSitter context, by way of motivation, let me say that, more generally, when one tries to study questions in quantum cosmology, you're immediately confronted with many conceptual issues. For example, what is the meaning and interpretation of the wave function? Because there's nobody outside the universe. So normally, if you have a wave function, you say, I compute probabilities, I go in the lab, I have an ensemble, and so on and so forth. You can't do that with the wave function of the universe. So what does the wave function of the universe mean? This is tied to who are observers, because they have to arise from internal, as from being part of the system. They are not external to the universe. How do we think of who observers are? What are the right observables? These kinds of questions you're immediately confronted with when you try to do quantum cosmology. Now, this is also in a sense related to the problem of time, and this problem pertains to the fact that there's no clock external to the universe. So especially when you're thinking about canonical quantization, we have space and time, we work on slices of constant time and so on. But here there's no clock external to the universe. So a physical clock has to arise from within the system, from among the degrees of freedom of the system. And then you have to do this thing which we never do normally in quantum mechanics, which is we take one degree of freedom or a set of degrees of freedom internal to the system, promote them to be clock variables, and then construct a Hilbert space at instances of that clock, and in that Hilbert space then compute the expectation values, etc., of other degrees of freedom. Okay, and how do you find such a clock? When can you do it? What are the choices? How does the resulting quantization depend on choices? These are all kinds of questions we don't normally have to deal with, but we have to deal with here in quantum cosmology. And the idea is that these conceptual questions are present also in 2 dimensions and are not directly per se connected with the UV divergences, which are of course present, say, when you're dealing with 4D gravity, with propagating graviton.
Does it mean that the time is somehow only semi-classically defined?
So it could mean that, and so a little bit one way to probe that is, let's say I try to use 2 different kinds of clocks, how different would be the description I get for the resulting quantum theory. Here what we will do in our talk is choose a physical clock, construct a Hilbert space, and you'll see that the resulting system is quite quantum. I mean, it departs from classical deSitter space and the behavior. But at late times, exactly, at late times a nice semi-classical limit emerges. And so what one expects is that, at late time, the choice of the clock will not change things too much. You choose one kind of clock, I choose another, etc. But at early times it might be different. Okay, so these issues are present even in 2 dimensions, and hopefully we can learn something about them and then apply our learning to more realistic higher dimensional situations. Okay, so that's the motivation. Now another motivation comes from holography, which is that holography is very poorly understood in deSitter space, but maybe in these 2-dimensional situations, which we can study thoroughly, and more generally, lower dimensional situations, 3 dimensions is also actually very interesting. The hope is you can really thoroughly quantize the system, understand it every which way, and then ask, is there a holographic description? And if it is, what kind of holographic description? Can we understand it precisely? And hopefully what you learn here again will translate to something of interest in higher dimensions. Okay, so that's the kind of motivation. Okay, so here we start with JT gravity. This is the action. Some of you have seen it. There is the 2-dimensional metric. Yes, there's the 2-dimensional metric and the dilaton, a scalar field which I call the dilaton. And let's see, in terms of dimensionless, there's only one dimensionful parameter, lambda. Lambda is taken to be positive. If you vary the dilaton, you see that the equation of motion sets are equal to lambda. If you take lambda to be positive, you get deSitter space. Okay, so we'll take lambda to be positive, and since it's the only dimension full scale, I set it equal to 2. that leaves only one dimensionless constant. G Newton is dimensionless in 2 dimensions. And what you can do, as you can see, because phi multiplies the whole bulk action here, r minus lambda, I can rescale phi to absorb G Newton. Okay. And that's what I'll typically do. And the thing to remember then is that the classical limit, which is G Newton going to 0, because G Newton is in front of the action, so it's like h bar. So the classical limit, G Newton goes to 0, if I redefine phi to be phi over Gn, then becomes phi going to infinity. Okay, and the very quantum regime becomes where phi goes to 0. Okay, but we'll keep that in mind, and we can then just rescale away G Newton. So this system has no, dimensionless parameters in that sense after rescaling. Now actually, there was a boundary term, the famous Gibbons-Hawking-like boundary term, which I didn't write down. But in addition, there's actually a topological term. As you know, if you just had root GR along with the boundary term, this actually just evaluates the Euler character of the manifold. So it's a topological term. And one should really think of the coefficient here, which weights different topologies differently, as being proportional to 1 over G Newton. For example, if you derive JT gravity in deSitter space starting from higher dimensions, then that's what you would get. Okay, that's what you would get, and actually it turns out, so the way you do that is a bit similar, if you know how JT gravity in anti-deSitter works, is that you take a near extremal black hole in deSitter space, say in 4 dimensions. It's called the extremal black hole is called the Nari black hole, and then you go to the near horizon limit of that near extremal black hole to come down to 2 dimensions. And when you do that, actually S naught is related up to factors of 2 to the entropy of the higher dimensional gravitational system. You have a black hole in deSitter, it's got a cosmological horizon, it's got a black hole horizon, the two are not very different, near extremality, and this coefficient is tied to that, and it goes like 1 over G Newton.
So here by near extremal you mean the cosmological and the black hole horizon are
come together. So it's actually a Schwarzschild black hole, as you were saying. It's not a charged black hole, but even a Schwarzschild black hole in deSitter has 2 horizons. You tune the mass to be close to the maximum, so to say, then you come to this limit. And if you think about it in terms of dimensional reduction, then this field phi, which I was referring to as the dilaton, is the radius of the internal space. Say the radius of the internal S2 if I was doing dimensional reduction from 4 dimensions. Okay, so this is useful to keep in mind, but as you'll see when we go ahead, we will then just take this system and think about it in 2-dimensional terms and not be too tied to this geometrical interpretation of the dilaton being a radius in higher dimensions. Okay, and the idea we'll explore as far as the problem of time is concerned is to take the dilaton to be the physical clock, to play that role. This is similar to what happens in inflation. As you all know, in say 4 dimensions, the universe, there's good reason to believe, went through a very rapid expansionary phase where it was close to deSitter called inflation, and there is a scalar field which rolls, slowly relaxing the cosmological constant called the inflaton. And one way to think about how the perturbations are produced is to think about them at constant values of this inflaton, and then ask about what are the perturbations and so on. And when you think about it like that, you actually are taking the inflaton, instances of fixed value of the inflaton, to be fixed instances of time. And here we'll do something similar with the dilaton. Okay, you could choose other clocks, but this is the, when we implement the canonical quantization, we will do that here. In dimensionally reduced, okay, now forget, so there is, so if it's the radius, then there's a minimum value. The radius can't get negative. It's not quite phi equal to 0 because the internal radius is shifted from the value phi takes by some constant. But anyway, it takes a minimum value, but we'll sort of be a little, for now we'll just go ahead, we'll try to quantize the system, and then we'll see what restrictions does it impose on the value of phi. Okay, and see, just more from a 2D setting, see where we go. Okay, so now let's turn to classical solutions. So this is global deSitter, and I've written it in these coordinates r and theta, because in these coordinates the dilaton just varies linearly with r. Okay, so up to a constant, which in fact I'll rescale away in the next slide, the dilaton is r. And this is the metric. Theta is a compact variable, goes from 0 to 2 pi, a is a constant, and so it's a very simple solution. Now, in terms of a Penrose diagram, this is the Penrose diagram of deSitter 2, and it is a rectangle. In higher dimensions, if you've seen the Penrose diagram, it's a square, but in 2 dimensions, it's a rectangle because theta, the angle variable, goes from 0 to 2 pi. These dashed lines are lines of constant values of the dilaton, which are also lines along which you move by these are killing directions, if you like. That is to say, you're moving by changing theta, or d by d theta is the tangent vector along those lines, because you're moving at constant r. You take the dilaton to be constant, you move along lines where you're changing theta, and theta is an isometry here. Okay, it's a space-like isometry because you have a time-dependent background. So these are those lines, and you go a distance 2 pi in the range of theta, and then you make an identification, and that's the Penrose diagram. Now, you see, when you look at it, one realizes because these dashed lines are isometries, nothing is changing in the geometry. You could also make an identification by not going a total range 2 pi. You can go less or more than 2 pi. That's also an allowed identification to make. The dilaton is anyway constant along these lines. The metric, this is a killing direction. The metric is not changing. So you can do that. And in this way, you get a host of solutions which correspond to taking the aspect ratio of the Penrose diagram to be different from the one here. Either you can make it, more oblong or more whatever, width or length can increase. So this is one entire class of solutions you get. And you can think of these solutions altogether as follows. I introduce a parameter m now. I rescale the dilaton so it's exactly equal to r. Rather, I rescale the coordinate r so it's really equal to the dilaton. And now there are 2 parameters which enter in the metric. The parameter a, which was entering earlier in the dilaton, appears in the metric, as well as this additional parameter m. And in the solutions I was describing to you, m takes negative values, and by changing m you get these different aspect ratios for the rectangle. Okay, and x here I've rescaled to be now compact, it was compact earlier, but instead of going from 0 to 2 pi, it goes from 0 to 1. Okay, so this is an entire class of solutions, very simple, just 2 parameters. Now you could ask, what if I take m to be positive? Here I took m to be negative to get that class of solutions. If you take m to be positive, what you get is are solutions which are orbifolds of black hole solutions in deSitter 2. So first let me start by describing the black hole solution, then I'll turn to the orbifolding. So this is the Penrose diagram for a black hole in deSitter, and it has 2 kinds of horizons, as was mentioned. These lines here are the cosmological horizons. So if you come from future infinity, you first will encounter one of these horizons, and these lines here are black hole horizons, black hole, white hole if you like. So if you come into this region, which is called the static patch, then you can fall into a black hole, or you could have come out here from a white hole and then make your way to the far future, and similarly for the past. Okay, so of particular interest will be the future and past Milne-like wedges and the black hole, white hole regions in our work, as you will see. If you look at the values the dilaton takes, it takes values infinity in the future of the future region and past of the past region asymptotically, and deep inside the black hole, white hole region, it becomes minus infinity. Okay, so this is a solution. Now, if you actually if you have m taking a general value, then what you really get is an orbifold of this solution. So I'll describe what it is. So these lines, let's take the future and past regions. These lines here, violet lines, are lines of where you move along the isometry direction. They are again lines of constant dilaton, like those dashed lines, but here they are the corresponding lines take this form, and for any value of m, what you do is you M and A, you go some length along the X direction, or rather you traverse some length along each of these lines and then make a identification. Okay?
Is there a reason why in the MG deSitter this R look like a timeline? Is there a reason why you're calling it R? Or is
I picked that for the other class of solutions, and the dilaton varies along R. So that's the way to think about it. That I've chosen a coordinate which I call R, but the physical meaning of that coordinate is that as it changes, the dilaton changes. So, but it is, you're right, it is a time-like coordinate. It's like with a minus, GRR is negative in sign. Yeah, somehow we chose that convention.
Is there an interpretation from the four-dimensional or the higher dimensional perspective of this transition from orbifolds to the usual bound solutions?
Okay, there's not a transition, but yeah, you could ask, what is the interpretation of these higher dimension, of these orbifolds in the higher dimensional theory? And yeah, that's something I'm not sure we would be so happy doing it in the higher dimensional theory. You can make the identification, but then you have to be more careful about, what happens, because now there's an orbifold singularity, which is a fixed point of the action, and you have to be more careful and ask, how does the system behave when it has this kind of time-like orbifold in its presence? And people have tried to look at questions like this some time ago in the context of string theory, and it's more involved because you've got dynamical gravity and so on. But you'll see that we'll be able to handle the theory. It won't be pathological with these kinds of identification.
Actually, in the next slide, follow up on Chetan's question. So phi was infinity at the bottom line, also at the
Top line, yeah.
So how is the time?
So phi actually, what happens is that phi is a proxy for, R is a proxy for phi, as I was saying, so it takes the value root m at the cosmological horizon, and then if you move in and move towards the other horizon, it decreases and becomes minus root m here at the black hole horizons, and then when you move further in, it decreases even further all the way to minus infinity. So that's the behavior.
I'm worried about the left side.
Oh, this side.
From future to from
Past.
to the future.
Uh-huh.
Phi seems to be not.
Monotonic. Yeah, so that's right. So phi is infinity, and then it hits root m, and then at the orbifold singularity, you jump across and go into the future Milnor wedge, and then it expands again. And that would have been true even if I didn't make the orbifold identification. And there what would have happened is that in a sense your phi would have, if you wanted to think about it varying continuously, you would go here and then go in there. And then it would, sort of be a more continuous thing. Okay, yeah. Okay, so now we have this orbifold singularity here, which is a fixed point of this identification action, and so this is like a baby version of a Big Bang singularity. Okay, so you can say, okay, I have this baby version of an interesting cosmology. It expands in the far future. It's rapidly accelerating deSitter space. If you go back, it has this kind of orbifold crunch singularity. The expanding universe is emerging from it, or in the far past, it goes towards the crunch. How is the quantum theory going to behave? Okay, so that's the kind of question you can hope to try and answer. Now, this region also, after you make the orbifold singularity, is a space-time in itself with the orbifold singularity, because null rays will, for example, will bounce back and forth. They don't leave the region. It's a conical region now. But this is another disconnected region you can get if you make the same kind of identification. In this region also, the dilaton, constant lines of constant dilaton are space-like slices, and as you go along them, you're moving along an isometry, so you can make identifications for different values, and that gives you a geometry inside with also, which is also conical with an orbifold singularity now at the bifurcate horizon of the two black hole horizons. In this region, lines of the isometry direction is time-like, so you really don't want to be making any identifications because you'll end up having closed time-like curves. So these are two kinds of disconnected, if you like, conical spacetimes you get if you look at the m greater than 0 branch. Okay, and we'll include them and we'll see, how does the quantum theory behave. And And sometimes I'll refer to the m less than 0 as the bounce branch, because it's like global ds. The universe comes in to a minimum value and then bounces back, and the m greater than 0 is more like a big bang, big crunch. This is just a very tame version of that big bang singularity, which is this orbifold singularity. Okay, and as a sanity check, you have 2 parameters worth of solutions, so the classical phase space of the system is even dimensional, 2-dimensional. So it's a really very, very simple system. Now it turns out these are not the only solutions, as was emphasized in these papers. And to explain, at least tell you what the additional solutions are, which we won't include in our quantization, and it'll turn out to be at least consistent in that if you take the system with the solutions I had in mind and quantize it, then the wave function will not leave those sectors. As you will see, sometimes interesting things will happen. I hope I have time. Where depending on how you quantize, you start with the wave function in this branch and it can leak into the black hole, white hole branch through some kind of quantum tunneling, but there won't be any connect with these other kinds of solutions. So at least it's sort of consistent to do, but just to understand the whole system, we should also include them, and I'll just describe what they are. That Penrose diagram I showed for the black hole in deSitter is not the maximally extended diagram. You know how these things work. If you look at, say, Reisner-Nordstrom black holes or something, you can get these maximally extended diagrams, and here what happens is you get the maximally extended diagram actually has infinite number of alternating regions, cosmological regions, and black hole, white hole regions. So after this you can tag on another cosmological region where the dilaton will asymptotically go to infinity, and then another where it goes to minus infinity, and similarly on the other side. So that's the full extended geometry. So here I've shown 2 sets of these. So the original cosmological and black hole region, then one cosmological on one side and black hole. But then you could have more and more. And their point was that now what you can do, and when you think about the symmetries and so on, it's possible, is you can take a point, say, or first let me start actually just with the original cosmological and black hole region. So you can just start with this, but now instead of making the identifications I was making along the isometry directions, make an identification by identifying a point on the left edge with the right edge. That's not going along an isometry direction, but it turns out the value of the dilaton at the 2 edges are the same, and the derivatives also take the same value, because this is going to connect to another cosmological region after that, which is not so different from this cosmological region. So you can make that kind of identification. It's allowed by the properties of the solution, and that gives you a 1-parameter family corresponding to how displaced the second point is compared to the first one. Or you can take 2 sets of these regions, alternating ones, and make an identity, etc., etc. So you get an entire branch of solutions like that, which we have not included, but which should be included to do the full proper quantization. So even this very simple system is actually kind of, it's a rich system. We should just try to think about quantizing it. Okay, but as I said, I think the number of parameters is still 2 that characterize these branches, but it's a little bit like, I'll have to check, but I think each of these, have come with 2 parameters, and one of them I've explained and the other one I've not explained here, but I think it's there, and let me get back to you. I don't remember exactly, but what I do recall is it's a 2-dimensional phase space for each of these sectors.
Sandeep, one more question.
Yeah.
So the wiggles in the theta direction, they are not allowed, or no, not in these solutions,
Mm-hmm.
in general, full class of solutions.
No, they're allowed. They're allowed because, after all, I was just drawing your attention to lines of constant dilaton, but of course the dilaton is evolving, and somebody else may choose to take different hypersurfaces, and that's certainly allowed. But here I was just telling you how we define the conical geometry in the first place, and after that, just for quantizing, we'll choose a particular notion of time, but you need not do that. For example, another way to quantize would be to take the extrinsic curvature to be constant along these slices. It's a little different, and so on and so forth. So the dilaton definitely wiggles, but you can, I was going to say that, but because the wave function is time reparameterization invariant, I can choose to evaluate it by doing local time reparameterizations on a slice of constant value of the dilaton. So that's the basic idea when we choose our clock. Okay.
In this general class of solutions, so the value of the deSitter number, both the time-like boundaries are constants?
Are constant, or are constant, this are the same constant, are the same constant, are the same constant.
By giving them, could you also twist them?
So this is the twist in a sense. This is the twist in a sense. So because it's constant and the same constant everywhere here and here, then you don't have to.
These twisted geometries will have good causality and so on.
Yeah, you can't send a signal. They are still space-like separated points, the 2 points. So you're not making an identification along points which are separated a long time. That's right. That's right.
These solutions have an extra parameter, right? Like the number of patches you're including, a discrete number.
Yeah, a discrete number. In each branch, I think you have 2 parameters, and then you have a discrete parameter saying which of these you're choosing. Yeah, some n or something. By the way, there's a very lowbrow presentation, but the most sophisticated presentation is to think of the deSitter group, which is in this case SL2R, and then think of the identifications by taking suitable quotients of that. And then instead of SL2R, you can consider some universal enveloping group, like we do when we look at ADS, where we unfold the corresponding group, and then you look at the expanded envelope, whatever group, and then make identification. Okay, but this is all it is. Look, guys, the geometry can be pieced together in the way I said. Okay, so this is lowbrow, but it's good enough. Okay, now an important thing is there's a conserved quantity here. This will be rather important. I'm calling it M. I might even call it the mass. That's a misnomer because, of course, we are working with closed spatial geometries. There's no ADM mass that would vanish. I'm just a mnemonic, and you can check in the classical solutions that both with respect to r, which is actually a time coordinate, and x, the spatial direction, m is a constant. Okay, and this constant there will be an analogous operator in the quantum theory which will commute when acting on physical states with the Hamiltonian, and that will be an important quantity for us. Okay, now something that will really help us, and then we'll really get going, is that the wave function of the Hartle-Hawking state can be calculated in using the path integral exactly, and this is a real help for us, even when we do canonical quantization, as you'll see. And the reason it can be done is because of a set of developments, first starting from JT gravity in anti-deSitter space, whereas some of you know Stanford and Witten showed that the partition function, okay, for JT gravity in anti-deSitter space can be computed exactly. It's one loop exact, and so you have to just do it at one loop, but there's a very good argument saying that that is exact. There are no further higher loop corrections in the path integral. And then in a quite a remarkable development, Maldacena, Turiachi and Yang argued that in fact you can compute the Hartle-Hawking wave function in deSitter space by analytically continuing the path integral from ADS2, except it's ADS2 with 2 time-like directions. Okay, now you really have to be worried about geometries which have 2 time-like directions, right? I mean, you really have to be worried. But they argued that yes, the path integral would be well defined, and in fact it would give the Hartle-Hawking wave function. So let me just elaborate on that. Usually we think of the Hartle-Hawking wave function also as being evaluated on metrics of a mixed signature, but the more conventional way to think about it is to take in 2 dimensions, to take a 2-sphere. Because if you analytically continue to Euclidean, then what happens to deSitter is becomes a sphere. So you take a 2-sphere, you chop it at the moment of, so to say, maximum size or time symmetry, which is in this case when it's a big circle on the 2-sphere, and then you glue on the Lorentzian geometry. Okay, and this is what gives us the Hartle-Hawking state. And if you want to evaluate the wave function, you would then say at late time you would evaluate it here for such a mixed signature Geometry. Instead, what was argued was that you can take minus ADS2 two time-like directions and do a suitable continuation which is allowed in 2 dimensions alone and come to the same wave function. Okay, and we were very suspicious about that. Okay, mathematically you can put in the i's and show that if you go from minus ADS with 2 minus directions, you do land on deSitter, but that's just some, doing things around. We were very skeptical, but indeed it turns out when you examine all the determinants in the path integral very, very carefully, okay, that in fact it turns out that there are branch cuts in, say, the R variable that I've been using as a proxy for time, but the branch cuts are safely away. The conventional Hartle-Hawking contour, say, to get to the expanding branch of the universe, takes you along this, and the Maldacena-Turiachi-Yang contour takes you along this, and you can argue, because there are no branch cuts, etc., that you land in the same answer. Okay, and this is true. We thought, oh, it's true even though you have 2 minus signatures, because there are no propagating degrees of freedom, you get away with 2 time-like directions. But then we did it even with matter, conformal matter present, and the determinants still have this structure that you only have branch cuts in the negative axis, so in fact you get the same answer even with matter. So this is a very funny thing. I can't say I understand it, but mathematically it certainly is correct, and you can show that you get the same answer from the S2 contour as you get from ADS2. Now it's minus ADS2, but that doesn't make in the end so much of a difference. The results of Stanford and Witten of ADS2, not minus ADS2, can be imported, you can show with control, to therefore obtain the Hartle-Hawking wave function exactly. Okay, and that's really helpful, as you'll see when we go ahead and try to do quantization. Okay, now I'm taking a little time, but that's okay, we don't have to go.
So minus ADS2 is a compact space, or is it a non-compact space? What kind of space? In the picture you have drawn, it was a compact space.
It's a compact space because it's one of these minus versions of a ADS black hole. So it still implements the no, that's an important point. It still implements the no boundary condition. So how does it do it? So first let's start with the black hole in ADS. And the black hole in ADS, of course, pinches off smoothly. Start in Euclidean ADS, then of course it smoothly pinches off given some size of the circle. The mass gets determined so that it pinches off. And now that's what happens in ADS, minus ADS2 also. And here you are specifying the length of the universe finally, and that correspondingly determines the mass in this minus geometry to allow for a smooth closure. So that's how it works. So here I've done it for just, where the asymptotic size is some 2 pi, but you can do it more generally. And then, you can do this, but more generally with a mass parameter, which would be governed, which would be related to the range of theta. You could do this also. So that's the idea. Yeah, it's quite interesting. It's quite interesting. They make this claim, I mean, I have to say, without evaluating determinants, I think they knew all about it, as is typical in one's case. Okay. So now let's go to canonical quantization. I'm going a little bit slow. I think that's okay. We don't have to rush through. I'll just say what the results are at the end. How much time do I have, by the way? Maybe like 15 minutes? Yeah, okay, sorry to be so slow. Okay, so I'm going to do very standard canonical quantization. Start with the 2-dimensional metric written in ADM kind of coordinates. N is the lapse function, N1 is the shift function. I go to the standard ADM gauge, set the shift function to be equal to 0, lapse function equal to 1. And now we have the equations of motion, as you know, obtained by varying n and n1, which are the Hamiltonian and the momentum. There's only one momentum here, and the equations of motion set these equal to 0. Okay, you can check that classically the constraints close, etc. And so it's it's a system you can hope to then quantize. Okay, now we go to the quantum theory. Let me say I work in the basis, position basis, so to say, where the wave function is a functional actually of phi and g1, which in general vary along, the spatial slices in general. And then the conjugate momenta are functional derivatives. Now the physical states must be annihilated by these constraints, okay? And so the task is to find all states which meet the Hamiltonian and momentum constraints, which are wave functionals of phi and G1.
Hartle-Hawking state is annihilated by this?
Will be annihilated, as you'll see. But there are a few subtleties which I'm coming to, but yes, exactly. That's the sanity check, actually, very useful, more than sanity check, actually, as you'll see. Now, it's not quite as simple because, as is well known, these constraints famously have various ordering ambiguities. So before we can solve for physical states, we need to say something about how these operators are to be defined. Okay, and this is the problem which sort of often bedevils such kind of attempts. Now there are ordering ambiguities, but also turns out there are UV divergences. Now these are of course much tamer than their higher dimensional counterparts, but they are still present, and they're present in the Hamiltonian constraint, it turns out, because the Hamiltonian constraint involves two momenta, therefore two functional derivatives, and at the end of the day that results in some kinds of singularities. So you have to deal with them as well as the ordering ambiguities, and what do you do? And so the way we'll proceed is as follows. First, as I said, we'll choose to evaluate that wave function, which is a functional actually, on slices of constant value of the dilaton. And the idea is this: suppose you had a more general slice where the dilaton was varying, say along this, is varying like this, and you've chosen that black slice. Now you can do local time reparameterizations. Okay, and move it to a slice which is the violet slice where the dilaton is a constant. And since the wave function meets the Hamiltonian constraint, it will take the same value on the black slice as it did on the violet slice. Okay, so you have not lost any information in that sense by just working on constant phi slices. So this is the idea. This simplifies things because now instead of a functional of phi, at least you have a function of phi, not a functional, but you still have to deal with the metric G1. But here we are helped with by the fact that we are working in just 2 dimensions. So the spatial slice is 1 dimensional. Now the momentum constraint, which tells us the wave function must be invariant vis-a-vis spatial reparameterizations, tells us that it can only depend on features of the 1-dimensional metric, okay, which don't change if I make coordinate transformations along that 1 dimension. And the only such quantity in 1 dimension on a closed slice is the length of the slice. Okay, so now the problem becomes very simple, having chosen such slices that the functional becomes a wave function of phi and L. Okay, and now the Hamiltonian constraint, there's still a non-trivial part to it which is left, which is in general called the Wheeler-DeWitt equation, now becomes an equation, a differential equation in the variables phi and L, which puts constraints on psi. But it turns out actually even after this simplification, the Wheeler-DeWitt equation is not uniquely fixed. There's still ambiguities, ordering ambiguities in it, and we need to fix those ambiguities somehow.
Is it reasonable to think of this L as you're making the G1 part of the metric constant on the slice?
Yeah, you can say that. You just choose a coordinate so that G1 is a constant. Exactly. Okay, now there's a usual approximation, as you know, everyone plays this game in cosmology, which is called the mini superspace approximation. You just put in the first place, say I'm going to reduce the degrees of freedom, just work with constant G1s, constant phis and so on. If you do that, you get a Wheeler-DeWitt equation which takes this form. And it turns out that the Hartle-Hawking wave function doesn't satisfy this equation. And we know the Hartle-Hawking wave function very well, we know it exactly here. Now, taken literally, if this equation were correct, that means that the Hartle-Hawking wave function doesn't satisfy the time reparameterization invariance constraint, which is a gauge constraint in the theory. Okay. Now, the Hartle-Hawking wave function is done by evaluating a path integral, which you can check and ensure is gauge invariant. You change coordinates, it's gauge invariant. The measure, everything which goes in is very carefully defined, it's gauge invariant. The only other source of breaking could be boundary conditions, but there are no boundaries here. So there's no leeway here. It should be that the Hartle-Hawking wave function is gauge invariant, right? So if that is the case, we have to change the Wheeler-DeWitt equation. But we know the Hartle-Hawking wave function not just semi-classically, we know it exactly, okay? And it turns out that allows us to really pin down the Wheeler-DeWitt equation exactly, okay? Because you know it, even if you know it asymptotically, you know it for all functions, all ratios of L over phi. you know. So there's a lot of information in the Hartle-Hawking wave function, and it turns out there's an additional term you have to put in. These two terms which were present in the mini superspace, they would be the ones which dominate in the semi-classical approximation. If you were very far in the future, universe is very big and so on, dilaton also becomes very big, so that's like h bar going to 0, you would only see these two terms, but there's an additional term which is subdominant in the WKB approximation, but it's important in general. And if you didn't know the Hartle-Hawking wave function exactly, you could not have pinned this down. This is an operator ordering ambiguity. It's an operator. So I could explain. So then after the fact, you can go back and ask what operator ordering would give this, and you can figure that out. But it's in the end answer analysis which comes from here. Exactly. Yeah. Okay, so now what we are going to do is take this equation to be the correct one, Wheeler-DeWitt, and now just find all solutions to it. Okay, so it is in the end a very simple problem, and here's what the solutions look like. This parameter m comes back. For a fixed value of m, you have two solutions. When you think about the momenta and all, this one is the expanding branch solution, that one, the other one is where the universe is contracting. M can take any value. The Wheeler-DeWitt equation is linear, so you can add these with any coefficients you want, and that gives you the most general such solution. Okay, and this m parameter corresponds to something that commutes with the Hamiltonian constraint on physical states. Okay, now I should really push on, but we are actually not done yet. We have the solutions, but we need to construct a Hilbert space, and that means we have to define a norm and so on in the space of solutions. And as I said, we are choosing the clock to be the dilaton. So we'll construct a Hilbert space for constant values of the dilaton, and try to define an inner product on this space. And because the Wheeler-DeWitt equation in the end is not so different from a Klein-Gordon-like equation, there's some correction, etc., but it's close, then the norm which is at least natural to define is this kind of Klein-Gordon-like norm. The reason why it's in terms of psi and not psi hat has to do with those differences. Psi hat satisfies a more conventional Klein-Gordon-like equation. So anyway, you can check that this is conserved, but it's actually, by conserved I mean it just doesn't change when phi, the physical clock, changes, but it's conserved if there's no leakage or flux at the ends. You know, if you have a system in some finite box or something, your probability might leak out. Here the finite box analog is that the length variable goes from 0 to infinity, because the length is a geometrical facet of the whole problem, right? The length of the spatial slice. So that can't get negative. So you can't have, if you want to have a conserved norm, you can't have any leakage from zero size universes. And that imposes a non-trivial condition, and that condition can be met by putting an analog of a Neumann boundary condition that d phi of psi is 0 along L equal to 0. And after that, you really have a conserved current, rather you have a conserved norm, and now you really have a nice Hilbert space. You know, you have the solutions, you have an inner product which is conserved, etc., etc. Okay, so now at this point you can say, okay, I understand the theory. The boundary conditions cut down all physical states by half, but you still are left with an infinite number. You began with m taking an infinite set of values, you're left with an infinite number even after this cut down. Okay, now I'm going to go a bit fast. Last thing, is not exactly a norm, it's more like a Klein. M takes all the values, I should have said that, minus infinity. So you're including both branches actually in this. Thank you. Now, actually, sorry, it's not quite a norm, it's more a Klein-Gordon-like norm, as in it can take a positive value or a negative one. So you have to sort of make a choice. You know, it's a little bit like the expanding universes will typically come with one choice, and the contracting ones will come with an opposite choice. But at least it's conserved. Now, depending on which universe you live in, you can choose that and then try to work with it and compute expectation values.
The constraint equation was not very, it didn't look like a Hamiltonian equation. It didn't look like the Schrodinger equation, right? It looked like a Klein-Gordon.
It looked, yeah. It's deeply connected to that. Right, exactly. And it's a known fact, when you look at even DeWitt's old papers on trying to do the quantization, the typical kind of norm you get on the space of metrics is more a sort of indefinite, that norm is an indefinite kind of norm. So, okay, now let me go fast forward if you don't mind. And what I'm going to do is jump over a few things and tell you about just a couple of things, which is, okay, so the couple of things I'm going to tell you are how to understand some of these other. So first of all, the Hartle-Hawking state you can check is a linear superposition of this type, okay, with a particular value of rho of m. Sorry to go back. So if I took the Hartle-Hawking state in the expanding branch, so you can write it like that. A rho m takes some particular value, okay, you can figure that out and so on. So that's a kind of course it had to be, because that's how we fix the Wheeler-DeWitt equation. But what about the other states? And can you understand them in terms of the path integral? And the answer is that to some limited extent. And the idea I want to especially mention this, Subrat is sleeping so early in the day, so let me say when he comes that here I was trying to highlight his work and that of some of the other collaborators. I don't know if they're here in the audience, okay, Chakravarti, Gode, Paul and Raju. And so what I'm going to do here actually is in a sense an implementation of their ideas, which you can be quite explicit about. And the idea is a very nice one. It is that, okay, for a particular theory, I get, if I impose no boundary, one particular state, the Hartle-Hawking state. But just suppose for a moment I could change the theory, okay, then, and I make a change so that the deformation dies away at late times, okay, in the semi-classical region. Then I compute the Hartle-Hawking state in the deformed theory. It should become some state in the original theory, because the difference between the two theories is gone away at late time, but it won't be the Hartle-Hawking state. This is the idea, okay. And that idea can be implemented. You can deform the theory by adding exponential corrections which vanish when phi goes to infinity, and show that what you get because of work done earlier in ADS, you can carry that out in the DS context and show that you get different coefficient functions. This is what the Hartle-Hawking state is, and then you get different coefficient functions and so on. You can get a large class, but we're not sure you can get all states. That's something we have to check, but you might be able to get all states like that. Now, this is a good way to generate the state, but it's only of some limited use. I won't get to it, but here we have studied the quantization of the universe in the single universe sector, which is what you can do in canonical. Then I'll stop in canonical quantization. But in the path integral, you can actually allow topologies to change, and you can therefore go from one universe to two through topology changing processes and so on. And this kind of deformation doesn't give you the right results for that. Okay, so it's a little bit like, anyway, so you have to be careful when you use it, but it does give you in the single universe sector an understanding of the wave function. Okay, last thing to say.
The wave function is supposed to be smooth through these across these.
So so let me, that's a good example, and I had it here. Just one minute. And so now that you have these solutions, you can go back and say what happens at the Big Bang. And you can take a nice, smooth, tight wave packet which behaves very classically far in the future, run it back, and it goes through the orbifold singularity where it's not classical at all, but then emerges in the far past as a nice, smooth, tight wave packet. So the universe really goes through this orbifold and emerges out, and so on. And there are more details about tunneling here and so on, which ask me later and I'll tell you, but it certainly does this. So that's what you get in the quantum theory. You get to follow it through very non-classical regimes. Thank you. Okay, now very, very quickly about holography. One line and then I'll end. It turns out that actually you can think of mapping these states we found. I gave a talk somewhere else for an hour and I had all this included, so I got ambitious. Okay, but just in terms of holography, if you take just this branch with m greater than 0 for a moment, that means the Big Bang, Big Crunch branch, then it turns out you can map these states, all the states for different values of m, without the cut down I put in, okay, due to no leakage of flux. They can be mapped one-to-one to states in a matrix theory. And let me just explain the idea there. And the idea is there. You have a matrix model, so this has not got any time at all. There's no concept of states at all in that system, okay? But you can think of the matrix as an operator acting on some Hilbert space. So you construct a Hilbert space out of thin air, in a sense, to explain the action of the matrix. And the eigenstates of that matrix, let's say those eigenvalues are m, then those eigenstates map in a one-to-one fashion to the states we found in the bulk, also parameterized by the parameter m. Okay, so there's a one-to-one map. The Hartle-Hawking state is rather special. It's like a trace. The other states are like generalized traces. You know, as you change that coefficient function, you have to change this function m. So there's a very beautiful map. And this matrix model is just the Saad Schenker Stanford matrix model studied in ADS, but here it appears with an imaginary temperature, okay, just because of the way deSitter space works. So I wish I could explain that, but there's a very nice map to a matrix model here, which is a very explicit hologram, and there are infinite number of states in the bulk, infinite number of states in the boundary theory, because the matrix is in the double scale limit. The hope is if we could extend this to the finite rank version, that would mean that then you had a theory of gravity with a finite number of states which are in one-to-one correspondence with the number of states in the hologram. Maybe this number of states has to do with the entropy of deSitter space, and then that would be a very, very nice explanation for the entropy. And you could either try to work with finite rank versions of these matrix models, or you could try to go up in one dimension for reasons I can explain, where you might expect finiteness more naturally, and that's what we are trying to do. If you go one up, and I'll close, if you go one up, it's very interesting. If you go to 3 dimensions, you can work with topologies which are time cross some Riemann surface, okay? And you have a choice of what these Riemann surfaces can be. The sphere is the simplest, but if you took the torus, okay, then it turns out that you can think of dimensionally reducing on one circle of the torus, and that maps to the JT theory. And the reason why we were getting things like L over phi is because this is the modular parameter of a rectangular torus. And more generally, the dynamics, the wave function is a function valued on the modulus of the torus. So it's a very beautiful story. But the simpler thing is the sphere. And on the sphere, you get a unique state when you solve the Hartle-Hawking, when you solve the Wheeler-DeWitt constraints. Because there are no moduli on the sphere and so on. You get a unique state. And it's very interesting to ask, how could it have an entropy? Can a unique state give rise to the entropy of deSitter space? And just to say, in terms of ideas I'd love to discuss with you, the other advantage in 3D gravity is that you have a Chern-Simons formulation. And so you could ask, if you had a Chern-Simons gauge theory on a sphere across time, and you are in the unique vacuum state of this Chern-Simons theory, can you get some kind of entanglement entropy by dividing the sphere in 2 parts? And the answer, as you all know, is yes. And so maybe that has something to do with the entropy of deSitter. That's what we're trying to compute. It's a natural kind of question. And if that works out, then of course, you know, I would be giving that talk to you. So we're still trying to calculate. Okay, sorry to rush at the end, but thank you very much.